radicals. And again, some of this, actually almost all of this, you guys should have seen in Algebra 2, even a little bit of it in Algebra 1. So first of all, square root. Hopefully we all know what that is. It's one of two equal factors. We have perfect square, which is the fourth definition down, so a number made by squaring a whole number. So like the square root of 36 is a perfect square because we can take the square root of it evenly. A cubed root is one of three equal factors, so the cubed root of 8 is 2 because 2 times 2 times 2 is equal to 8. We have our radical symbol, which this one here we are used to. It has an index of 2, which means square root, but we don't ever have to write the index of 2. If it is something other than 2, and I guess I should, the number that goes here is the index. This is the radicand. Okay. So if it's anything other than 2, we do have to write it, like cubed root, fourth root, fifth root, all of that. And that's actually how we say it. We say square root for 2, cubed root for 3, and then after that, it's just the fourth root, fifth root, sixth root, the 100th root. We just say whatever value that is. So along with a perfect square, a perfect cubed is a number made by cubing a whole number. So again, cubed root of 8 would be 2 because 2 times 2 times 2 is 8. All right, here's a whole bunch of properties. So they're very similar to the properties of exponents, but with radicals. So let's take a look at them. So the first property is if I have the nth root of a to the m. That just means, notice how the first part, the m is under the radical. The second part, the m is outside the radical. So it just says it doesn't matter what you do first. I could raise it to the m power first and then take the square root, or the second part says I could take the root first and then raise it to the exponent. And you're probably thinking, well, what does it really matter? Well, sometimes it's easier to do it in your head if you do it one way versus the other way. So for this first example here, if I have the cubed root of 8 squared, well, if I square the 8, then I get the cubed root of 64. And because I've been doing this for a while, I know what the cubed root of 64 is off the top of my head, but until you guys go through some of this work, you may not. And so it might be easier to switch the order, put that squared outside the parentheses like we have here. Because the cubed root of 8, that's one we get to know pretty regularly, so that's 2, and then I take 2 and square it and I get 4. So a lot of these are just ways to be able to do the work inside your head a little bit easier. Obviously, you always have a calculator, but you're going to see here a little bit later when they ask us to just simplify, stuff like this is a little bit easier because we don't want the number answer. Property number 2 here just says if you have several radicals with the same index, you can put them all under one radical if we're multiplying. Okay, same with division, so we might as well do 2 and 3 together. So the nth root of a times the nth root of b, we can simplify that to the nth root of a times b. So here's the example with the numbers. The square root of 5 times the square root of 7, we can put it all under one radical as the square root of 35. Same with division. If I have the fourth root of 27 divided by the fourth root of 9, if I'm looking at this like, oh my gosh, I can't do the fourth root of 27 or the fourth root of 9. I don't think that comes out to be even. But if I write it under one radical, I can do the fourth root of 27 divided by 9. Well, then I'm able to simplify 27 divided by 9 to give me 3. So that whole expression simplifies to the fourth root of 3. Okay. Rule number 4, it says if I have 2 radicals, I can combine them. And I'll show you why here in a second. Do you guys remember how to write radicals as exponents? Because that's super helpful. So if you have like the square root of 5, that's really 5 to the 1/2 power. And we are going to have a lesson where we go over this. So, but I'm just going to show it to you to explain why we can put those 2 radicals together. So if I were to do this problem here, that would be 10 to the 1/2 to the 1/3. Well, using properties of exponents that we worked with on Friday, a power to a power you multiply, so that's 10 to the 1/6 power, which is the 6th root of 10. So if at any point these radicals start to get confusing, sometimes it's actually helpful to write them as fractional exponents, which you probably never thought you'd ever say that doing something with fractions makes it easier. But in this case, it does. So that's why we are able to multiply those indices together, because 3 times 2 automatically gives us our 6 there. Okay. The next property, it's what we've been doing. If you have the square root of a squared, those exponents, the exponent and the radical, cancel out, and we are just left with what's underneath. Here's the kicker, though. When we have our index and exponent being even, okay, we really need to take the absolute value. And here's why. Because if I have the square root of -12, I'll just write it down here like we have it. If I were to do this, whoops, it's squared. Square root of -12 squared is positive 144. Because when I square it, it becomes positive. When I take the square root of 144, I get 12. Okay? Technically, we would get plus or minus 12, but you're going to see why we just need the positive here in a second. The rule says I can switch these two. So -12 squared. I can't really do that right now because it's a negative under the radical and we can't take the square root of negatives. So that's why we need to make sure that when these cancel, we end up getting the positive value. Okay, so if it's an even number, an even index and exponent, make sure you take the absolute value. On the contrary, if it's an odd index or exponent, we keep the negative, because I can take the cubed root of a negative. Negative times a negative times a negative is a negative, so that negative remains. All right, so simplifying radicals. These are a couple things we need to make sure we keep in mind. Radicals are in simplest form if all factors have been removed from the radical. So there's no like perfect square factor hanging out under the radical. All fractions have a radical-free denominator, and we do this by rationalizing the denominator, which you guys are going to do tomorrow. I will have a video for that lesson posted where we're rationalizing. And the index of the radical is reduced if we're able to do that. So let's take a look at our first example here. Square root of 20. Now, before we get started, square roots, I'm going to write some magic numbers here because I know when you learned this previously, you probably made factor trees, and I'm just going to tell you we need to sort of get away from those factor trees because it's going to take us a long time. So let's see if you can tell me, you stop me when you know what my magical powers are here.
Perfect squares.
Perfect. They are perfect squares. So it's 11. There's 12, 13, 14. Whoops. All right, I'll stop there. At least if you know up to 15, that's a pretty good start. Sometimes 16 gets in there. And then eventually we'll work with the cubes too. We don't have to get too far into the 4th and 5th exponents, but sometimes the biggest one they use for the 5th exponent is 2. So you'll know that 2 to the 5th power is 32 because they use it so often. So we're going to say, okay, I'm going to look at these numbers over here, and the square root of 20, well, that falls right here. So I just need to try all these numbers below where my line is. So is 20 evenly divisible by 16? The answer, no. Is 20 evenly divisible by 9? No. Is 20 evenly divisible by 4? Yes, it is. So I'm going to break 20 down into the square root of its factors, one being 4, the other one being 5. So all I'm doing is breaking these numbers down into something where one of the factors is a perfect square, which is not always possible. So then, technically, I'll show it here, we would do the square root of 4 times the square root of 5. using this rule right there. The square root of 4 is 2. The square root of 5 I can't do. So then we're done. All right. So part B, it's up to you guys how you do this one. I'm going to show you 2 ways. Eventually we start to get to know our fourth roots, or even you could get a calculator out and say, okay, 2 to the 4th. Yes, I should put like, whoops, squared up here. I'll do x to the 4th here because you do get to know some of them. So 2 to the 4th is 16. Wow, we're already at pretty high. 3 to the 4th is 81. So we're already past 48. So our only option is to see if 16 works. So 48, oh, it is evenly divisible by 16. So we could break 48 down into 16 times 3. The 4th root of 16, well, that was 2 to the 4th, 3 to the 4th. So we get 2 times the 4th root of 3. So we'll just leave it at that for now. All right, and the last one, the first thing I see is, hey, that has a 4th power, that's a 4th index. So that means they're going to cancel, but because it's even, I need the absolute value of 5x. So this we can only simplify a little bit. I would be okay if you stopped right there with your answer. To me, that's sufficient. Technically, though, we can do one more thing. And that is, I can take the actual absolute value of 5. I can't take the absolute value of x because we don't know what that value is. So if I take the absolute value of x and just write x, I'm taking a chance that there's going to be a negative in there. But 5, absolute value of 5, no matter what it is just 5. So technically, we could write it like this, and that is the best answer. But I would accept the other one. Okay? You just have to make sure if it's an even index, even exponent, that you put the absolute value bars. All right, simplify. So we have the cubed root of a whole bunch of stuff here. So I'm going to break down my 24. So if we wanted to, I have a calculator handy. I'm going to do 2 to the 3rd power to write all these. So these are x's to the 3rd. So I always start with 2 because 1 is just 1, and that's not very helpful. So 2 cubed is 8. 3 cubed is 27. And like I said, these first couple, you guys will get to know. 4 cubed is going to be 64. Just typing them in my calculator to make sure I'm not leaving you astray. 5 cubed, I believe, is, it's 125. I was going to say 225. 6 cubed, actually, I think if you get to 5 on this one, you're pretty good. But 6 cubed is 216. 7 cubed, we'll stop here at 343. They don't tend to give you anything higher than that for cubed root. So 24, well, that's evenly divisible by 8. So I'm going to do the cubed root of 8 times 3, because that's my 24. Now when I have letters, I like to write these so that their exponents are in groups of 3. So a to the 4th, that means I have one group of 3, so I have a cubed, and then I have one a left over. And now we're going to take the cubed root of everything we're able to. The cubed root of 8, that simplifies to 2, so that is outside my radicand, or my radical symbol. Cubed root of 3, can't do it, so that's going to stay there. Cubed root of a cubed, well, that just gives me a. Do we need the absolute value bars there? For the cubed root of a cubed?
No.
No, perfect, because it's odd index. Right, so that's gone. And cubed root of a, can't do that. So that's our answer. All right, the next one, I'm going to go and do the way that you guys probably learned a long time ago. So the negative, actually, anytime you see a negative underneath an odd index, you can automatically pull that out. You don't have to worry about it because a negative will come outside the radical. So negative cubed root, and then I just like to write this. I just can't forget it. It needs to stick along with my problem. So I'm going to do this the old way. So 40, I'm going to break that down into 4 and 10. 4 is 2 and 2. 10 is 2 and 5. So those are all my prime numbers, right? A to the 6th is just going to mean I'm going to have 6 A's. So let's write this up. I'm going to put my negative out front. There's my cubed root. 2 times 2 times 2 times 5 times 1, 2, 3, 4, 5, 6. And it's okay to start off this way, but I really want you to try doing it like we did A. So this one now means I need to have 3 of them in order to pull them out. So I have one group of 3 2s. There's a group of A's. Oh, there's another group of A's. So the only thing that's going to be left under my radical sign is that 5. Everything else is coming out. So I have one group of 2s. I have 2 groups of A's. So that's A times A, which is A squared. And then underneath, I have the cubed root of 5. Do you guys remember doing the problems like that at some point?
Yeah.
So I'm okay if you do that, but I'm telling you they're going to end up getting much larger. And then eventually, if you look down here at example 3, we're actually going to be combining terms. And so we have to break each of these down. So like that problem we just did, there's going to be several of them. And notice at your turn, there's 3 and 4 terms. So that process gets a little bit lengthy at times. So that's why it's good to start to get into the habit of knowing what perfect squares and perfect cubes are. Okay. All right. Are we ready for example 3? Combining and simplifying. I think we just have one more after this. All right. So the only way we can combine radical terms is if they have the same index and the value under the radical, so the radicand, is exactly the same. Meaning I would have to have the cube root of 5 plus the cube root of 5 to be able to actually add them together. So think of what's under the radical as exponents, or not exponents, variables. So if I had, whoops, let me change this. If I had 2x minus 3x squared, would I be able to combine those two terms together?
Oh, wait, no, you can't.
No, we can't. But what if it were 2x minus 3x? Could we put them together?
Yeah.
And what would our answer be? Negative 1x, right?
Yeah.
So did we do anything with the variables? No, we just sort of left the variable there. We combined the coefficients. Keep that in mind for this problem. So let's simplify, reduce what we can. Square root of 48. All right, off to the side. This one's easy. We can do this. So 4, 2, 3, 4, 5. I'm going to stop when I get to 48. 6, 7. Okay. So 48 is evenly divisible. Oh my gosh, I can't talk today. Divisible by which of those numbers? And I want the biggest, because if we don't choose the biggest number it's divisible by, then we end up having to do this process again.
$16.
Perfect. It is 16. Okay. So I'm going to break this down. Let me erase this stuff over here. 2 on the outside. Square root of 16 times 3. All right. So that's the first one. Oh, that's a huge minus. Don't quite want that. Minus 3, 27. Well, 27 is actually going to be here. So I went from those numbers down. So 27, well, 9 right away. So I think 9 and 3. So 9 times 3. Now simplify each. Don't forget, there's already a 2 out here. So when I take the square root of 16, I'm going to have 2 times 4. Minus 3 times square root of 9. Well, that's another 3 times the square root of 3. Right, now simplify. So we get 8 root 3 minus 9 root 3. Now this is where we look and say, okay, are we able to simplify this? And the answer is yes, because the square root of 3 is the same as the square root of 3. So now I just have to do 8 minus 9, which is negative 1 square root 3, or we could just write negative square root of 3. All right, problem B. This one is cubed roots. Erase this because I don't need the square roots. So cubed roots. So I want something that is x cubed. You guys are lucky because there used to be a section in this chapter where you couldn't use a calculator, but that is now out the window. We won't be doing that. So 2 cubed is 8. 3 cubed, I swear we just did this, is 27. Oh, we did. I just have it somewhere else. I wasn't looking in the right spot. Maybe I erased it. I think I did erase it. It's okay. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. I'm pretty sure 7 cubed is 343. I'm just going to double check myself here so that I don't give us wrong answers. Okay. But none of ours even go up that high. So we have 16 and 54. So 16, it's going to fit right here. So it's clearly divisible by 8. So I'm going to rewrite this as the cubed root of 8 times 2x minus, now 54 fits right here. And if I take 54 divided by 27, oh, I get 2. So this one's going to be the cubed root of 27 times 2. I have 4 x's, but my index is 3, so I'm going to break them down into groups of 3. So x cubed times x. Okay, so now let's simplify each one. Cubed root of 8, that is 2. I cannot take the cubed root of 2 or x, so that's going to stay under my radical. Minus cubed root of 27, I can do that, that's 3. Cubed root of x cubed, that's just x. And then underneath my radical, I still have the cubed root of 2x. Now, one thing I will say, please be careful. Do you notice how I always put a space and I make sure that my 3 is inside that little radical there? Because we don't want to make that index look like an exponent accidentally. All right, this problem is one where a lot of people get confused. And if I told us that we could stop there, we'd be good. But this is why people get confused by it. Notice how my radicals are exactly the same. So we can simplify this. And I want you to think about simplifying this like factoring in a way. So if I were to simplify this, I would take 2 minus 3x times the whole thing, cubed root of 2x. That there is our best answer because I rewrote it in simplified form. We did the exact same thing I did for part A, except I can't actually subtract the 2 minus 3x. But it is super important that you put them inside parentheses. Otherwise, it will look like 2 minus 3x times the cube root of 2x. But really, both of them. Got it. So let's recap. We have simplified basic radicals. We have simplified slightly more complicated radicals. We have added and subtracted radicals. Our last thing to do with them is to multiply them. So there's 2 different types of multiplication here, radicals. First thing is if I have one radical multiplied by another one. Notice how there's only multiplication there. Part B, notice how I have, there's 2 radicals being added, there's 2 radicals being subtracted, and then I'm multiplying them. So over here on the right, I actually have a binomial of radicals. And so this binomial, what if I had like x plus 2 times x minus 4? How would we simplify that? What's that process called?
Foil.
Right, so we're going to end up foiling this one over here. Okay, so I feel like that one's pretty easy. Some people don't like it because it can get a little bit messy, but if you take your time, it's just foiling, so it's pretty simple. This one here, honestly, probably has to be my least favorite problem, just because the numbers get so large, but other than that, it's not difficult. So for this one, a couple things we have to look at. First of all, before we can even multiply these two together, they have to have the same index. And do they have the same index? They certainly do. So now I can multiply everything together. So I only have one radical to deal with. So multiply things that are like, so my 5 and my 2, they're just coefficients out front. So that gives me 10. And then under my radical, I'm going to have 100 times 10 times a squared times a. So now let's simplify this. 100 times 10 is 1,000. A squared times a is a cubed. So if we look, this actually doesn't turn out to be too bad. The cube root of 1,000. Does anybody know what that is?
10.
Perfect. Because 10 times 10 times 10 is 1,000. So that works out to be a 10. So don't forget that 10 plus the 10 from the 1,000. Cubed root of a cubed, that's just a. So now if we simplify, we get 100a. So that one wasn't too bad, but the numbers can get a little bit larger. All right, we ready for this next foiling problem? I'm going to make it big because this we'll do stuff like this throughout where we have to foil things that are not so nice. So you might want to get used to this process. Oops, sorry. Okay, so I'm going to erase all this stuff. That way we don't get anything confused. All right, and I'm actually going to write foil on here. So for this first example, I'm going to write out every single step. I know that once you guys do this, you're probably just going to be like, oh, I'm going to multiply those two together. But bear with me here. I'm going to write out all the steps so you can see it. So the first one is my 2 root 3 times 3. That's my F for my foil. All right, so I did my first. I'm going to do my outside 2. Oh, I see a negative there, so now this is going to be minus, or maybe I'll just do plus and we'll worry about the minus later. So plus, I have 2 root 3 times negative square root of 3. So that's my O. Plus, now I have to take 3 root 5 times 3. So 3 root 5 times 3. That's my I. Plus 3 root 5 times the square root of 3. Don't forget that negative. 3 root 5 times negative square root of 3. And that's my L. So it looks rather complicated, but it's pretty easy to do this. Now multiply the things that we're able to multiply together. So here I can multiply my 2 and my 3. So this simplifies to 6 root 3. I have a plus and a minus, so this is going to be minus now. Let me erase that one. There we go. So 2 square root of 3 times the square root of 3 is the square root of 9. I'm going to leave it at that for now. Actually, I'm going to rewrite this so that it's directly underneath. plus 3 times 3, so I have 9 root 5 there. I have a minus here, so minus 3. I don't have another number out front. And then here I get the square root of 15. All right, so now we have to look at each of these and say, okay, is there anything we can simplify? So square root of 3. I can't simplify that, so that one's going to stay 6 root 3. Minus, oh, square root of 9, I can do that. So that's 2 times 3. Can we simplify the square root of 5?
No.
No. So that stays 9 root 5. Minus, can we simplify the square root of 15? Well, 15's only factors are 5 and 3. Can I take the square root evenly of either of those?
No.
No. So, gosh, that stays there. Okay, so the only thing I can continue to simplify is 2 times 3. So I get 6 root 3 minus 6 plus 9 root 5 minus 3 root 15. And that's our answer, because we cannot combine anything together. Square root of 3, square root of 5, square root of 15, they're all different radicals, so we can't combine any together. I can't simplify anymore, so we are done.